The next topic that we have is flow visualization. So let's take this example. So this is an example from this book, Fox and McDonald. So this is an example of a flow pattern for flow around a car mounted in a wind tunnel. And this has been generated by releasing smoke. So by releasing smoke into the flow at 5 fixed upstream points. This visualization is done to get a better understanding of how the flow takes place. Okay, so let's understand what are the different types of flow for visualizing the flow patterns. Okay, so there are three ways for obtaining the flow visualization. The first one is called by tracing the path line. The second one is by tracing by constructing the streamline, and the third one is by constructing the streak lines. Okay, so let's understand the first thing, path line. The first way of visualizing the flow patterns, that is by constructing the path line. So let's understand what a path line means. So path line is the path followed by a fluid particle in motion. So actually this fluid particle, instead of writing fluid particle, let's say write by a tiny fluid element. So generally people write it like fluid particle, and they say that the particle is not actually the real particle, but it is in fact a small fluid element, so that the continuous approximation still holds true. Okay, so instead of writing particle, let's just write a tiny fluid element in motion. Okay, so it's actually a Lagrangian description of motion. Like we described the fluid in Lagrangian description, the same is the case here. So what we do is we take a tiny fluid element and then we observe how it moves in space in time t. Okay, now a question can come into your mind that how can we do that? So the answer is we can do this using tracer particles. So what are these tracer particles? So tracer particles are tiny particles that are injected in the fluid they are such that they can be visually distinguished from the background flow and are tiny enough so that they don't disturb the fluid flow. Okay, so we inject tracer particles inside our fluid, and these tracer particles can be like some dye molecules. So these are tiny enough so that they don't disturb your fluid flow and can be visually distinguished from the background flow. Okay, so we inject the fluid with these tracer particles, and we observe how those tracer particles move over time. And thus, by studying that, we can construct the path line, or we can get the path line for that fluid flow, right? Okay. So next is streamline. So streamline, it is an imaginary line within the flow, so that if we construct or if we draw a tangent on the streamline at any point, then that tangent will give us the velocity, the instantaneous velocity vector at that point. Okay, so now in the streamline we are not concerned with the individual fluid element. Okay, instead what we are concerned with is the flow at a particular point. Okay, so that's why this is kind of a Eulerian description. Okay, all right, so let's say if a streamline is given to you, let's say this is a streamline that is given to you. So what can you say about the instantaneous velocity vector, let's say at this point? So we just said that the tangent constructed, so tangent constructed on this streamline would give us the streamline was like this. So the tangent constructed on this streamline would give us the velocity vector. So this is the instantaneous velocity vector at this point. Similarly, this would be the instantaneous velocity vector at this point, and this would be the instantaneous velocity vector at this point. Okay, so I hope this concept is clear to you. Okay, so this is a Eulerian description. So how we actually get the streamline? So let's say inside a fluid, so let's say this is a container and the fluid is inside this container, and we have a large number of probes at different points. So let's say at this point we have a probe, at this point we have a probe, at this point we have a different probe, at this point we have a different probe, and at a certain instant t, this probe measures some velocity vector v vector, this probe measures some velocity vector v vector. Let me just define it in this sense. So this measures velocity vector like this measures velocity vector like this measures velocity vector, let's say like this, and this measures velocity vector like this. Okay, so then we can construct a streamline by drawing a line for which these velocity vectors are tangent at this point. So it would look something like this. So it should go, let's say something like this. Okay, so I hope this concept is clear now. Now let's say this velocity vector is v vector, and consider a differential element on this streamline dr. Okay, so now what can you say about the this value v vector cross dr vector? What would be this? This would be, of course, this would be 0 degree. This would be, of course, 0. Why? Because v vector and dr vector, the angle between them is 0 degrees. Okay, right? So this cross product would be 0. Okay, so let's write v vector in terms of the orthogonal axis I hat, j hat and k hat. So let's say this is vx, let's say this is vy, let's say this is vz. So this is how I can write v vector. Then I have dr vector would be given as dx I hat plus dy j hat plus dz k hat. Okay, right? Now since v cross dr equal to 0, we can write this v cross dr, we can write this dv cross dr like this: vx, vy, vz, dx, dy, dz. This determinant should be 0. So I can just open this: I hat vy dz minus vy dz minus vz dy vz dy minus j hat vx dz vx dz minus vz dx plus k hat vx dy vx dy minus vy dz vy dx. Okay, this will be 0. Okay, now let's simplify this expression. So the first term, now since this, so this is a vector quantity, this has to be 0 vector, and this 0 vector can be written as 0 I hat plus 0 j hat plus 0 k hat. Okay, now comparing the magnitudes along various directions, we will get this term equal to 0, this term equal to 0, and this term equal to 0. Okay, let's write it. So we have vy dz minus vz dy equal to 0. So I can just take, so it would be like this, and I can take this here, so I can write this as this. Now similarly, I will have vx dz equal to vz dx and vx dy equal to vy dx. Okay, all right. So now can I have some further simplification to using these three equations? Okay, let's see. So this gives me dz upon vz equal to dy upon vy. This gives me dz upon vz equal to dx upon vx, and similarly this gives me dy upon vy equal to dx upon vx. Now using these three equations, I can just write dx upon vx equal to dy upon vy equal to dz upon vz, right? So this is the equation for a streamline. Okay, so now let's say a v vector is given to you in the question and you want to draw streamlines. So we can use just this equation to get the function which corresponds to the streamlines. Okay, so let's understand this with one example. So let's say a question is given to you. So let's say it is given that the v vector in your space, it is given as kx I hat minus ky j hat plus 0 k hat, and this k is a constant. Now the question is, draw the streamlines. Okay, so comparing this v vector with v vector equal to vx I hat plus vy j hat plus vz k hat, I get vx, I get vy, and I get vz. Okay, now what I'll do is I'll use this equation. So vx is equal to kx, the magnitude vx is kx, vy is minus ky, and vz equal to 0. Okay, so now this equation for the streamline is dx upon vx, vx is kx, should equal to dy upon vy minus dy upon ky, should equal to dz upon vz. Now you may say that, oh, this vz is 0, so this will become infinity. No, it's not the case like that. The reason is, when I am deriving this equation, I took a finite vz. Okay, now let's say vz is 0, this will become 0, and I'll not have vz in this expression, in this equation, and thus I'll actually not get. What I will get is, I will get this as 0, wherever is vz I will get this as 0. Okay, so then what I will get is, I will get, okay, let me just check it again. Yeah, so then I will get vy dz equal to 0, vx dz equal to 0, and I will get this equation. So the only equation which will be useful now would be this equation. Okay, and I will not get equation 1 and 2. Okay, so let me just erase this. Okay, so then we only have this equation to play with. Okay, so now how will you solve this? K gets cancelled out with k, then I will just integrate both sides, and this will become ln of x, this will become minus over ln y plus some constant c. Alright, so I can take ln y this side, this will become ln of x plus ln of y equal to c. Now we have ln of ab is equal to ln of a plus ln of b. So using this equation, I can write ln of xy, ln of x plus ln of y, I can write as ln of xy, this will become equal to c. I can take ln this side, this will become e to the power of c, and e to the power of c I can write some other constant, let's say c1. Okay, so then the equation is xy equal to c1, with c1 positive. Why c1 would be positive? Because e to the power of some constant will always be greater than 0. Okay, alright. Okay, with c1 greater than 0. Alright, so the streamlines in the positive or in the first quadrant, so this, let's say this is y, this is x, the streamlines would look like this. Okay, so from the velocity vector, we are now able to derive how the streamlines would look like. Okay, so these are my streamlines. Okay, for v vector equal to kx I hat minus ky j hat. Okay, the third way of visualizing the flow is streak line. So what is a streak line? So streak line, it is a curve which gives an instantaneous picture of the location of the fluid particles which have passed through a given point. Okay, so how can we understand it? So let's say in a container, or not, let's not take a container, let's say there is a pipe, okay, and there is a fluid flowing inside this pipe, okay, and now let's say from the using a small needle, I am injecting tracer particles from this needle, okay. Now depending upon the fluid flow about this point, this tracer particles would follow that trajectory, right? So let's say my fluid flow was like this, okay, at that instant, then the tracer particle injected from here would go like this, then after some time it would be like this, after some time it would be like this, okay. So the path that is covered by these tracer particles, this path is called the streak line, okay. Now it could be the case that let's say I injected one particle and the particle, let's say, flows, this particle after being ejected from this needle, let's say this flows like this, okay. So after a time t, the particle is over here, then let's say the flow is not steady and the next particle that was injected from this needle follows some different trajectory. So this was the earlier trajectory of this particle. The next tracer particle, it follows some other trajectory, let's say it goes like that, and the third particle, let's assume that it goes like that. So then in this case, this would be my streamline, okay. So this is the difference between the streamline, streak line and path line, okay. Let's understand the difference among these three lines from a nice YouTube video.
Initially, at time t equal to t0, flow field is totally horizontal and the fluid is moving in horizontal direction. In a similar fashion, flow field at some other instant of time, say t equals to t1, looks like this. At any point on the domain.
So let's say that these dashed lines are the streamlines, okay. Now they will tell me what are the instantaneous velocity vectors in this space, okay. So now at t equal to 0, let's assume that the streamlines are directed like this, okay. The velocity vectors are like this, so the streamlines would look like this, okay.
Local velocity vectors is always tangential to these gray dashed lines, and hence these lines are known as streamlines. Here, one can observe that the streamline pattern are different at two different instants of time as the flow is unsteady. This is the picture of the same flow field at another instant of time, say t equals to t2. You can see that a red particle which was at point O at time t equal to t0 have currently moved to point A following the red path in the domain, and hence this red line is known as the path line corresponding to the red particle. In the similar way, one more particle marked in black color was located at point capital O at some earlier instant of time and have currently moved to this point of the domain following the black path, and hence this black line is known as the path line corresponding to the black particle. In the same way, particle pink have moved here and particle green came here. Here one can observe that the relative positions of all these four particles at the current instant of time is different, but all these particles have earlier passed through point O of the domain, and hence the line joining these four particles is known as streak line corresponding to point O. So here grey dashed lines are streamlines, blue line is a streak line corresponding to point O, and red, black, pink and green lines are the path lines corresponding to red, black, pink and green particle respectively. I hope with this example you got a...
So it's what is happening in this case. I think that would be more clear if I go so if I go sometime backward in this video, we can see how the streamlines are actually changing from t is equal to t naught. I don't know what t he used, so from t is equal to ti to t is equal to tf. Okay, so in time tf minus ti, let's say the streamlines change like this. Okay, and the particles they enter from here. Okay, so now in time tf minus ti, they would follow this trajectory. Okay, and just go forward in this video. Let's just play from here. So this is how the particle moves in this flow field. Okay, so this is just focus on this red point, how this red point is moving. So this red path, the red curve is the path line for this particle. And now let's say in this time tf minus ti, I am injecting more particles from this side. Okay, so then in this time the particles would go like this. So the black, so there is another particle after red which moves like this, then there is another particle which is green. Okay, the next particle is pink which goes like this, and similarly the green particle. Okay, so now this and this, these are the path lines, because they tell the actual motion, the actual trajectory of the particle going from t is equal to ti to t is equal to tf. So in time tf minus ti, what is the path followed by the path taken by the particle? Okay, so these are the path lines. Okay, the streamlines are these gray dash lines. Okay, they are telling me what is the flow field at a fixed point. So let's say if this is a fixed point, what is the flow field at this point? So these are the streamlines. And what is the streak line? Like I said before, the streak line is found by joining these particles. So so when these particles were injected, the same way is done for the same method is followed for constructing the streamlines, and that's why we can get the streamline here. So this curve is the streamline, is the streak line. Okay, so I hope now the difference among these three is clear to you. Okay.